So, to start us off, the definition of velocity, if you do remember, is x2 minus x1 over t2 minus t1, which is equivalent to delta x over delta time, or change in position over change in time. So, if that's the definition of velocity, then how can we make this instantaneous? Well, first, let's put it graphically, because it's very much simpler to visualize this way. Let's say I had a person moving with the y-axis being representing his position and the x-axis representing the time. And he were to move somewhat like this. This would be his, he starts off at this position, decides to move down for some reason, and as time goes, he decides to go up in a quadratic fashion. Let's say I want to find his average velocity from x1, t1 I meant, here, t1, to here, t2. To do this, I would have to define the points. So I'll go here. So I'd go here and here and draw a line between them. This would be to find the average velocity between these 2 points. For some reason, this line is not working. There we go. So that's how you find the average velocity, is by finding the slope of this line, because x2 minus x1, which is the change in y, over the change in x, which is t2 minus t1, gives me the slope, which we should have learned in grade 9 maths. However, what if I want to find, at t3 here, what if I want to find his velocity here? Like, not in comparison to another point, I want to find it by itself there. How would I do that? So, the way you'd have to do this is you would have to, first think approximately, okay, so I have t3, and I want to find exactly there. Okay, what if I define some t4 that's really close to t3 and found this velocity, the velocity of this line right here. Okay, so I find that slope. The closer and closer I bring that dot, or t4, to t3, the closer it ends up being to the actual instantaneous velocity of t4. And so we can define this by a limit, which, if you remember the previous function, it would be that the instantaneous velocity is equivalent to the limit as delta t approaches 0, because we want the change in time to be 0. But we have to compare it to something, so let's make it approach 0 in this case. And of our previous function, which is of delta x over delta t. This ends up actually being a derivative. This is dx over dt. So this is the differentiation of x with respect to time, or we can call this x prime of t in Newton's notation. For example, I have someone's position is given by t squared minus 4t plus 4. This is someone's position. It's defined by this function of time. How I would find his instantaneous velocity at, let's say I were to ask you, how would I find his instantaneous velocity at 2 seconds? So, how I would approach the problem is I would take the derivative of this function, so dx by dt is equivalent to 2t minus 4. So this is the instantaneous velocity with respect to time. And then I would plug in the 2 seconds. Equals to 0. So it actually, and funny, I didn't even plan this out. I just put up a random function that his instantaneous velocity at that point does end up being 0. So yeah, that's how you end up calculating for the instantaneous velocity of a of yeah, no, in general, that's how you calculate it.